Welcome to part 4 of these talks about the three fundamental laws of circuit analysis, Ohm's law and Kirchhoff's voltage and current laws. This time, the bad news. None of these laws work in real life. Well, that's a bit of an exaggeration, perhaps. They all work to some extent, but it's important to know that they are not perfect, and there are exceptions. And throughout your studies, you will come across examples of circuits which do not obey these three laws. And it's important to be able to recognize them. So we'll start with Ohm's law. What's wrong with Ohm's law? Ohm's law states that the current flowing through a conductor is proportional to the voltage across the conductor. Let's have a look at that in the simulator. Here we have a resistor, which is the component that we're interested in, our conductor if you like. The voltmeter is reading the voltage across the resistor, and the ammeter here is reading the current through the resistor. So if we plotted the voltage across the resistor against the current through the resistor, we would expect a straight line, because that's what Ohm's law says. The voltage is proportional to the current. Let's see what happens. Yes, looks like it works. All of these points lie on a straight line, so the voltage across the component is proportional to the current flowing through the component. Things are looking good for Ohm's law. Except, what happens if it's not a resistor? We could replace the resistor with, let's say, a light-emitting diode. And now let's try it. Again, plotting the current through the component against the voltage across the component. It's not a straight line. It really isn't. So for this component, the voltage across the component is not proportional to the current flowing through the component. This component does not obey Ohm's law. Back when Ohm was doing his experiments, he didn't know about light-emitting diodes. He wasn't able to do this kind of investigation in the lab. So when he stated his law, that the current was proportional to the voltage across a conductor, he wasn't aware that there are some devices which conduct electricity, but for which the current through them is not proportional to the voltage across them. And light-emitting diodes, in fact any type of diode, is a very good example of a component which does not obey Ohm's law. There's another problem with Ohm's law, even when you apply it to resistors. And that is that Ohm's law, which says that the voltage across a conductor is proportional to the current flowing through it, only works if the resistance of that conductance is constant. And for all real resistors, that's not true. All real resistors have a temperature coefficient. The value of their resistance, in other words, the ratio of the voltage across them to the current flowing through them, is a function of temperature. And resistors, when current flows through them, dissipate heat, which means they get hot, which means their resistance is changing. So even for a resistor, which in theory should obey Ohm's law, in real life they don't quite obey Ohm's law. I'll do a numeric example. Supposing we had a resistor of value 1000 ohms. I'll write it as 1K. And I put 10 volts across that resistor. Then a current of 10 milliamps would be flowing through that resistor. Now, if 10 milliamps is flowing through the resistor, and there's 10 volts across the resistor, then the power being dissipated by that resistor is 10 volts times 10 milliamps, or 100 milliwatts. Now, supposing that I increase the voltage across this resistor so that it's now 100 volts. if there's 100 volts across this resistor, then Ohm's law would suggest that there should be 100 milliamps flowing through it. We've increased the voltage by 10, the current should increase by a factor of 10 as well. However, that would mean that the power being dissipated in the resistor would now be 100 volts times 100 milliamps, or about 10 watts. 10 watts is quite a lot of power. It's going to heat up that resistor. And as that resistor heats up, its resistance is going to change. Most resistors increase their resistance as the temperature goes up, so perhaps this resistor, once you start trying to dissipate 10 watts through it, may go up to 1010 ohms. If it's 1010 ohms, with 100 volts going through it, then the current flowing through it is no longer 100 milliamps. It would actually be 100 volts divided by 1010 ohms, which is about 99 milliamps. So we've increased our voltage by a factor of 10, but the current has only increased by a factor of 9.9. And that's due to the fact that the resistance of this resistor has increased because the resistor has been getting hot because of the additional power that's being dissipated in the resistor. In practice, this isn't a big problem, because you can buy resistors which have very, very small temperature coefficients that don't change their resistance very much at all with increasing temperature. But it is important to note that this effect will always be there to some degree. Ohm's law works perfectly for perfect resistors. But there is no such thing as a perfect resistor. And there are a lot of components which do not obey Ohm's law at all. Next time, we'll have a look at what's wrong with Kirchhoff's voltage law.